Let's for a moment consider the intersection of this surface with the YZ plane. Okay, so in YZ plane we have x equals 0. Now if x is 0, what does the equation become? Well, the equation becomes 9y squared minus z squared equals 36. Putting this into standard form, we're going to end up with y squared over 2 squared minus z squared over 6 squared equals 1. Again, I'm not going to go through the details of that rearrangement because we want to see what happens. Now we know that this is a hyperbola. And we can draw the rectangle representing this hyperbola in the YZ plane. Now we'll put y here, we'll put z here. We have to move up 6 units in the z direction and down 6 units. Not very evenly marked, but we see it will come down to here and up to about here. And in the y direction we'll come over 2 units. Looks like I've got a slightly bigger scale in my y direction, but let's go ahead and sketch the rough rectangle that we get. To graph a hyperbola, as we know, or should know, we sketch this rectangle, we sketch the diagonals, which are going to be the asymptotes of our hyperbola, and then we determine whether the points to the right and left or the points to the top and bottom are actually on the graph. Now, we can let z equal 0 on this graph, and it's possible to find the y that works here. In other words, if y is plus 2 or minus 2 and z is 0, it's easy to verify that this equation is satisfied. Whereas if y was equal to 0, we would have a negative equal to a positive, so that's not possible. That tells us that the point of that the vertices of this hyperbola lie at y equals plus and minus 2. At the points in the YZ plane, the points 2, 0, and we'll indicate that those are YZ points, and YZ equals negative 2, 0. Again, we can verify that both of these points satisfy this, and there is no way that the y can equal 0 because there would be no z value that would make the negative equal to the positive. To sketch this hyperbola, all we need to do is start at the vertex and come out in a shape that might be reminiscent of a parabola but isn't a parabola, and becomes asymptotic to the asymptotes. Okay. Now we can write out the equations of these asymptotes. We've already written out the equation of the hyperbola, but we see how this hyperbola is oriented in the YZ plane. If we come back then to our original picture, well, here's the YZ plane. What do we have? We have the point 2, 0 in the YZ plane, and in fact we have, well, we don't have the same rectangle, but the, excuse me, I'm searching for the right pen here. The hyperbola that we just draw does go through the point 2, 0 in the YZ plane, as indicated, and comes up and moves away from the z-axis. We could sketch the corresponding rectangle, 6 units up here, 2 units over here, and the asymptotes, but the sketch would get very confusing, and it probably already is. But we can see that if we go from this point to this point, that's exactly what might happen. We come along here and we curve out this way. And over on this side, we go from this point to this point, we would come up and very plausibly curve outward, intersecting this point and this point of our upper ellipse. Similarly, if we look at the xz plane, we would find that, running out of colors here, we would find that we would again get a hyperbola, and that hyperbola we could easily verify would go through these 2 points and these 2 points. So the hyperbola would sort of look like this. And we begin to see how this is sort of a funnel shape, but the funnel is narrowing more and more gradually as we approach the xy plane. Also, knowing what a hyperbola does, we see that we would come down like so, and down here we would come down in a similar manner in the yz plane, and do something very similar below the xy plane, so that our shape would start to widen out again.